Making a video. So, physics. And we're at the Yale guy again. Shankar. I can't remember his first name. But anyway. And he's going to do it again with this slit problem. And so I'll show you the MIT single slit thing just because it's an adequate visual of it. And I probably should have a double slit somewhere, but I don't, so tough. Anyway, so let's play a little bit of this, and I'll point out what's really wrong with it.
All the momentum, all the energy of that electron. That's exactly what particles do. So when you encounter an electron, it is simply a particle. So where does the problem come in? Where does the quantum mechanics come in? It comes in when you do the famous double slit experiment.
Okay, so again, pointing out that somehow this is the magic of quantum mechanics, and this demonstrates something besides, you know, how you can pervert any kind of evidence. You know, that's what it seems to me to be, just an example of how you can pervert them through interpretations. So anyway, he's pointed out that, yes, you have this, things end up landing someplace, and it seems pretty certain that it's landing as a clump. It's not a wave. It doesn't spread out. It doesn't do any of the other stuff waves do. And yet, quote unquote.
That's the key. The entire quantum mystery is in the double slit. Part of the resolution is in the double slit, but the rest are a little more difficult, and I'll try to tell you. First, I want to tell you.
Okay, so you're hearing it right out of the horse's mouth, so to speak. They're relying on this experiment to be demonstrating something about the nature of moving bodies through moving, you know, or through past other material substances that have a character of their own. And again, I would just argue that it seems kind of obvious to me that even just from the Earth moving around the sun, there's an invisible force, right? There's something happening. The Earth doesn't just fly right by the sun. Something happens because it's next to the sun. And the closer it is to the sun, the more that something happens. And it just seems that applying the same rules to saying, well, we're going to figure out where something's going to go based on putting matter next to it, and then see if it still goes straight. And logic would say it probably isn't going to still go straight. Just the logic of the solar system, for example. It's just not a very good way to test where something is to put matter and say, let's try to brush up against it. Doesn't work. Yeah, it changes where the thing's going to go. But it doesn't change our knowledge. So anyway, the whole Heisenberg thing basically is saying that the light going between my eye and the camera, your eye and the screen, isn't going straight. It isn't a straight line at a constant speed. They're going to tell you, essentially, through quantum mechanics, that it can't be known. That if I take the halfway point and I calculate the speed of light, that I can't know exactly where the photon is. And of course, I can know it theoretically. But if I try to detect it personally, if I try to catch it, or grab it, or photograph it, that ain't going to happen. Because there's no instrument to do that with, except big clumsy ones that are going to change where it's going to go. That's not that complicated. You don't need any magic.
What goes wrong with Newtonian mechanics? After all, if everything is a particle, what's the big deal? What's the problem? The double slit experiment is a problem. That's what puts the nail on the coffin for Newtonian physics.
Right, and again, I would argue that only because you all completely ignore the obvious, which is the photon or the electron will go somewhere different depending on how close it is to the matter you're shooting it through. So the closer it is to the surface the more it will get diffracted, and the further from surfaces, the less it will get diffracted. And you're basically saying that simple observation somehow isn't worth even considering. It's not even worth consideration. It won't be given a second, a millisecond, any consideration whatsoever in the conversation. It will be just ignored completely, and discount it as if that couldn't possibly have something to do with it. When, logically, one would surmise it could possibly. Yeah, seriously, it really could possibly have something to do with it. Yeah.
And here it is in basic version. You got two slits. By the way, I'm going to call the particle the electron. They're all doing the same thing.
Okay, they're all doing the same thing. So this idea that all particles are light, photon is the same as an electron, is the same as a hunk of matter. No, it isn't. They're really nothing alike in so many ways, in fundamental character. And so electrons are charged. They don't travel necessarily in very straight lines. They have a lot more going on in an electron than in a photon. And that casual statement of just saying it's the same thing is just wrong. It's like comparing a fish to a school of fish. You see how a school of fish can wobble and sway and do all kinds of things, where the regular fish kind of doesn't. It just kind of goes this way or goes that way or goes this way, but it doesn't just wobble around in space.
So one applies to one, applies to all of them. There is a source like an electron gun that emits electrons. In the old days, televisions had the electron gun. And the gun emits electrons, they go hit the screen, they make a little dot, and then the dot moves around.
Again, just, so casual, so let's just pretend we don't have to take any of this too seriously. And let's understand, the electron gun can't emit something that moves any kind of direction. You had to have big magnets to steer the electron to the right location. Very powerful electromagnet in the back of your TV to control the direction of the electron. Kind of a significant point here is that electrons are easily controlled in a sense. They're easily deflected by a field of magnetism.
And you see your favorite show. Okay, this is the electron gun. An electron gun has been engineered to send electrons of a definite momentum.
So a definite speed.
That you can get by accelerating electrons over a definite potential, and the gain of so many electron volts will turn into kinetic energy.
Right, which gets a little bit complicated because as much as they say the electrons aren't being shot at a frequency, they sort of are, because they sort of trick the electrons by putting electrical potential. So they have a negative and a positive, and so the electrons shooting towards the positive and then make the positive go away. So the electron's momentum takes it right past it. Kind of that kind of thing has to be used. Otherwise, the electron would slow down and come back and hit the anode. So the only way to really fire them is you do have to turn the cathode on and off. I think that's the right way. And well, one of them.
As for direction, if this gun is really far away to the left, in principle 1 mile, then the only way electrons are going to go 1 mile and hit the screen, they're all basically moving the horizontal direction.
Right. By his own theory, though, they could be going, and you could just have one that just happens to end up here, and it went on a slope like this, and so it could be going in this direction. But never mind that.
Then you put a row of detectors in the back, which will detect electrons. Then this is slit 1 and this is slit 2. You block slit 1. In fact, let me say the following thing.
You did this in the first video too. I don't know exactly. It's just a kind of a lack of a continuity thing. Like, I was going to get to it, and then no, let me throw in this little bit first.
What do we really know when we do the experiment? Once in a while, this gun will emit an electron.
All right, this is kind of the boring part. I mean, just going to say, a gun and it lands in a location. Well, I'll let him say it, but I mean, it's the boring part. I just want to get to
we know it's emitted the electron because it'll recoil.
Drawing.
One way, just like a gun, rifle. It'll recoil. That's when we know the electron left. Then we don't know anything, and suddenly, one of these guys, it says click. That means electrons arrived here. This is what we really know. Everything else you say about the electron is conjecture at this point.
Well,
You know, it was here.
conjecture based on patterns of reliable patterns, which are that these things tend, okay, to keep going in the direction they're going. That's one of these basic rules of inertia, is that unless something changes its direction, it goes in straight lines. That's the way things travel. I can throw a rock into space, and the rock's going to go straight unless something affects it. So, well, I'll let him just do it. No point in saving a minute by making a mess here.
You know it was there. Question is, what was it doing in between? Now, if you say, look, things cannot go from here to there except by following some path. I don't know what path it is. Maybe if it's an ordinary particle like Newtonian particle.
Well, I'm just saying we do, though, know that unless it's flying through an atmosphere or something and has wings or it could do something, it's going to travel straight in most of these circumstances unless there's some reason for us to believe it doesn't do that. And we know that for photons anyway, the straightness is pretty well demonstrated in just about every case possible, except when you put the photons next to matter. And that with most particles, you have to you can understand where it's going to go based on the fields that exist around it. So if you control the fields, you'll control where it goes.
Take some straight line, hit that slit, or go to that slit and arrive here. So you might say, I don't know the trajectory, but it's got to be some trajectory. Maybe like that.
Well, that's the kind of the argument, though, is that we do know that the only way it got there is it went through one of these holes and it came and landed there. And there's specific places that it has to go through here to end up here. If it goes right through the middle of this thing and doesn't get diffracted, well, then it ends up over here. And if it's close to this side, then maybe it can go over here. But if it's close to this side, it might end up over here. So we can know something. We can surmise based on where in this slit it goes through. May be a place to look for an effect, okay, that changes the effect.
Or maybe like that. So the electron takes some path, and you can label the path as either through slit 1 or through slit 2. Okay, now here is the problem. Suppose I do the experiment with slit 2 blocked. So you cannot even get through this one. And I sit at a certain location for a certain amount of time, maybe 1 hour, and I see how many electrons come. And I get 5 electrons with only one slit open. And if I move that observation point, I get some pattern, pretty dull, looking like that, and I'm going to call it I1. That's the count.
Okay, so he did it again, so to speak. And later he's going to change this when he does the single slit without the double slit, and then he'll use this big bulge and this 2 little tiny humps, and he'll say, just ignore those, but I'll jump to that. So anyway, so so this is what, again, he's just doing this there's no pattern thing with one slit blocked and one slit open. No pattern. Now, the only way you can have no pattern, this slit has to be really, 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 really tiny. That's it. And what that means is that this diffraction is really, really, really spread out. So I'll show that, and then you'll understand what I'm talking about. And such. So this is MIT, Professor Lewin, with the green lasers, I recall. And it's not loading very well. Come on, YouTube, help me out here. Doing science. Come on, science. Do it for science, YouTube. For science. Display the video, please. For the science. Sake of science. Please. Oh, dear.
The size of the bright spot is now entirely dictated by the divergence of my laser beam. The diffraction width is negligibly small because A is very large. But now watch. Now I'm going to tighten.
Okay, he just said the diffraction width is very small, so he's basically arguing. Okay, so he has a wide opening, shooting a laser beam through it. The laser beam just goes straight through and makes a dot. He's arguing that there really is a pattern in there. You just can't see it.
Make A smaller. I'm doing that now. I'm making it smaller and smaller. The diffraction which is still negligible.
Alright, so now you can see that the two slits are now, the sides, the surfaces are now becoming more and more relevant because they're starting to encroach on the beam. And so now parts of the beam are now hitting the surface. No surface up here, no surface here. These two surfaces are coming in, and this is spreading out. Okay, seems kind of logical.
It's smaller. I'm beginning to see the dark lines. The diffraction.
Now, that's single slit. Clearly not negligible amount of light coming off these two sides, not meaningless, invisible, you can't see it. It's quite obviously there. Quite obviously. Big, big, big there for that. It's there. It has there-ness. So, depending on the width of the slit, you get lots of pattern. Alright, now as you go smaller and smaller, this pattern, now that you've created it, so that's the trick. You come in, there's no pattern. You come in, the pattern arrives and starts expanding. And the real trick is it's just going to keep expanding as you get narrower and narrower. But they're going to call that something else.
Which is taking over. Look at the center.
So, okay, the slit's getting narrower and narrower, and what's happening is these spaces are getting bigger and bigger. That's all. They're getting longer and longer.
Maximum, right there. It's getting wider.
Alright, so, but clearly, still, very strong pattern. No doubt about it, it's there. The interference. What all the physicists, as soon as they see it, they go, that's an interference pattern. Yeah. See, so how does that fit with this? This. So we just pointed out that a single slit can produce on lots of pattern here. And he just said, no, it doesn't. Because what he's doing is, how did I lose it? Oh, I put it over in this new window. He's doing this.
It's getting wider. And I make the slit narrower. It's getting wider.
Now, what do you think's really happening here? Do you think this stuff isn't here anymore? Do you think all of that disappeared? Or do you think, because the slit's now 1/10 of the width of before, that much fewer photons are going through? And so the only ones reflecting in a visible way are these. But that if you went further, there'd still be if I put a time-lapse film here, or I put regular film, there's a blob here, and there's a blob here, and there's a blob here, and there's a blob here. It's all still there. It's just been spread out.
It's getting wider. Look how beautiful you see these destructive interferences, where light plus light gives darkness.
Right? Light plus light. It's a single slit. Light plus light. I mean, single slit in the sense there's only one photon that went in, but somehow light plus light makes darkness. I can't, yeah, sorry, but that's just, I mean, that's just not very good rhetoric.
Wider. Wider. Right now it is at least 10 times wider than it was before.
Right, it's 10 times wider, which means the slit's probably 10 times narrower. So the slit's got narrower, the pattern's spreading out. So that's the principle. But the principle is this pattern obviously is still here. It just you can't see it because as you make the slit smaller, less and less photons are going through, and it's getting weaker and weaker and dimmer and dimmer. And that's why you don't see it. And so combine that with what this guy's doing, which is he's basically saying, yeah, well, let's make this slit really tiny, and then we can spread this way the hell out. Okay? But is that really what the double slit experiment does? Or do they make the width much bigger than that? So he's not doing the math for the actual experiment. So he's discounting the possibility that this slit's plenty wide enough to be making a pattern, and that pattern could be a duplicate of a dark spot and a light spot. But more likely, the fact is that it's the changing in the field lines that are going to change the patterns. The patterns aren't going to line up because of that. In terms of comparing a single slit with a double slit, you'll have different field lines because you have a different width of the opening. So if you use the same width, you'll probably get the same openings. I guess that would be my argument. The same pattern. But he's not doing that.
It's a function of position up and down the wall of detectors. Then I repeat the experiment with this guy closed and that guy opened, and I get another count. Looks like that.
Okay, so as pointed out, that's
that's
not what you're going to get. So I'm just going to show it one more time. Okay, that's not what you get. Okay, what you get is depends on when you decide to what the dimensions you choose. You choose different dimensions, you get a very different pattern. Just emphasizing the facts.
I2 when 2 is open. It's I1, it's I2. Now I'm going to open the 2 slits, and I'm going to pick a particular location. It doesn't happen everywhere. I'm going to pick one location called X. But I used to get 5 electrons per hour with one thing open, and 5 electrons per hour with the second thing open. Now I want to open both and ask what will I get.
All right, now this is an experiment that hasn't been done. So he's saying this is what I'm going to, he knows the answer, and he knows the answer only through math. He doesn't know the answer through an actual experiment. I mean, I should, should say something like, whoa, that ain't right.
In Newtonian mechanics, there's only one possible answer to that question, and that is 10. Because we got 5 this way, they got 5 that way, and you open both. Whoever is going this way will keep going that way. Whoever is going this way will keep going this way. They will add up to give you 10.
So it seems an experiment that they should have the technology to do. I mean, if we just saw a single slit with a variable opening. So it seems like it wouldn't be too hard to put another opening next to it, okay, that didn't vary. And then you could play around and try different things and see how the pattern changes based on having slits of different widths next to each other. And that might tell you something. But none of those experiments will be part of this conversation. No variations on the experiment will be part of this conversation because, in my opinion, they're extracted because they might indicate something else is the cause. Yeah.
Now I told you, some people may say, well, maybe it's not 10 because with both slits open, maybe someone from here can collide with someone from there. And how do you know that?
Well, again, we know that doesn't happen. So that whole colliding thing we know doesn't happen. We know photons don't collide. Now, if you want to say electrons collide, okay, fine, but we already know the experiment's pretty consistent and photons don't collide.
That'll happen. So I'm saying, do the experiment with such a feeble beam of electron. There's only one electron at a time in the whole lab. It's not going to collide with itself. Then you wait long enough, and you have to get 5 plus 5 equals 10.
Well, you're going to make it collide with itself by making it copy itself and then collide with itself.
What I'm telling you is if you go to the location marked X, so you got 5 with each one open. When you open both, you will get 0. You don't get anything.
Okay. So I'm just saying there's no proof of that. So there's no, I won't find a YouTube video anywhere. I won't find anything anywhere where there's any proof that you have 2 slits, you cover one of them, and a place that was light becomes dark. There's not a single video that'll make that happen. That'll show you that happening. And I think the reason is because obviously I think you can. There's indication that you're going to change the experiment as you change the experiment. But whatever.
That is a great mystery. That is the end of Newtonian physics.
Okay, so the end of Newtonian physics is an experiment that's never been done. Okay, so that's good enough for you people, right? So the experiment that's never been done ends Newtonian physics. And we will not ever discuss the fact that if I randomly shoot things through an opening, okay, I randomly spit through the hole in my hand, there's an odds that I'll hit his head, and there's an odds that I'll hit my hand. Yeah, we know that. Things will go through that pattern based on odds. And the simple argument is the closer it goes to my hand, the more likely it is to be diffracted. And it's going to be diffracted based on field lines that emanate and bend. And as you push the things together, you compress the field lines, which means they have to bend at a sharper angle, which means the electron moves at a sharper angle, the field electrons, and therefore the diffraction pattern becomes wider as you compress the slits. Seems a perfectly viable explanation for the physics, and we don't need to pretend photons are waving or that electrons split in half. Big electrons split in half and go through both slits. We don't have to pretend any of that stuff anymore. Alright, I think that's enough. I have to sew this together, so I can't be too big a file anyway, so I better stop there. But anyway, I'm just saying, every time you see one of these blobs, I could show him where he does it again. I mean, there's a blob later in here. I probably should get to that one, because when he does that one is when he negates the meaning entirely of the, okay, yeah, here it is.
You will observe this particle
See
anywhere
the
in this
little
angular
blobs?
width.
So he just says ignore these little bumps. So these little bumps represent the diffraction in the single slit experiment. So he just says pay attention to this, totally ignore all of these. And that's somehow valid, or sensible, or rational, or meaningful, or any of those words. So he just basically got rid of all the rest of he got rid of the pattern by just making the central maxima, spreading it large enough that he just makes it the only thing that exists. So that's all he did. He just did this. He just moved it along, compressed it enough so he could make the pattern go away, and all you have is that. So we know the pattern's still there, but he just said let's just get rid of it. Let's ignore it. Because that makes our quantum mechanics make more sense. Because if we don't ignore it, then we have to somehow explain how the two slits are doing, the single slit's doing exactly what the two slits are doing. And they don't want to deal with that in a rational manner. Alright, well that's enough now. Okay. So, till next time.